First problem on the second exam asks you to apply the definition of convergence to show that the sequence 4n over 2n plus 5 converges to the limit 2. And the hint that I give is that for all natural numbers, the quantity 4n over 2n plus 5 is actually less than 2. So my question is, how does that hint actually help? Where do you use this hint in the process of writing this proof? The basic structure of the proof mirrors the definition of convergence for a sequence of real numbers. And the last clause in that definition asks you to justify why the absolute value of Sn minus L, which we'll fill in what that is here in a second, why that is guaranteed to be less than epsilon once we've defined n in this way and we've chosen arbitrarily a little n which is greater than or equal to that. Right? So we won't do out all of this algebra, but how the hint is useful is when you substitute for Sn the definition in terms of n for that sequence, 4n over 2n plus 5, and you substitute for L the limit, 2, we get a quantity that looks like this. And one of the important steps in your algebra, which you probably had to do this in your scratch work as well, is we have to somehow get rid of the absolute value signs in order to rearrange this inequality and understand what it tells us about n, rather than about the absolute value of n. So knowing that this quantity is less than this quantity, what does that tell me about how to get rid of this absolute value? Because the first of these addends is less than the second, when I subtract, I'm going to get a quantity inside the absolute value, which is negative. And when a quantity inside an absolute value is negative, what happens when we take the absolute value of it? Yeah, it flips sign. It becomes its opposite. So here's how I'm going to wrap this up here. I'm just going to write that as minus the quantity 4n over 2n minus 5, 2n plus 5 minus 2. Right? So because the quantity inside is negative, the absolute value is equal to the opposite. Right? And so it gives us this extra minus sign, which, if you like, also has the effect of switching around the subtraction. So here the hint, how the hint is useful is it helps us to get rid of the absolute value sign, both in the scratch work that you did to figure out how to define this n, and then also in the algebra that you do as part of the proof, to show why this construction and this assumption will guarantee that Sn minus L in absolute value is less than epsilon. So the second problem asks you to debunk one claim and then modify it in such a way as to make it true. So we have this study partner named Steve, and I particularly chose this name so that nobody in our class is named Steve, has discovered a new theorem such that if I have any two sequences and one of them converges to 0, then when I multiply the two sequences together, he claims that that's going to make the product converge to 0. And so the first task here is to figure out why that is in fact not a true statement, by demonstrating that there exists a pair of sequences which meet the hypothesis. They're sequences of real numbers, and the SNs converge to 0, but which do not satisfy the conclusion that SN/Tn converges to 0. And then the second part of it is figuring out how to add one more condition, not to S, but to the sequence Tn. So what additional condition can I add to the Tn sequence such that this will actually be a true statement, and then we'll be able to prove it. So without giving away too much on this problem, maybe just draw a quick diagram. So let's suppose that I diagram out my Sn sequence. And my Sn sequence has to be a sequence whose terms converge to 0. So maybe, as I usually do, I'll just depict that as this sequence that just sort of decreases monotonically to 0. So maybe those are my SNs. So then the question is, in order to debunk Steve's claim, we need to find a Tn, and another sequence Tn, that has the property that when I multiply it together with this Sn, the result is a sequence which no longer converges to 0. So we somehow have to compensate for how quickly these terms are shrinking by multiplying them together with something which is not shrinking, something which is getting larger. Specifically, if we want to debunk this claim, we need to multiply it by a sequence which is growing more powerfully than the SNs are shrinking. Right? So this is one of these tug-of-war kind of things. Irresistible force meets immovable object. We need to yank the values of Sn up away from 0 by multiplying them by the Tn's in such a way that that yank away from 0 persists as we go out towards infinity. So maybe what we're looking for in our Tn's is something which grows kind of quickly. That if these are my Tn's, then the idea is that when I multiply the two of those things together, I need to get a sequence which, maybe the sequence that you get still converges, it just doesn't converge to 0. So one of the things you could think about doing is there a way for when I multiply these two terms together that I get a really nice, well-behaved sequence? Maybe one that still converges, but no longer converges to 0. That's one way you could go about this. Another way you could go about it is by choosing a Tn that grows so quickly that it pulls all of the Ans up so that they don't even converge anymore at all. So you could make an example where the Ans diverge to infinity. They properly diverge. So that's up to you. Either one of those is going to be a counterexample that shows that Steve's theorem is in fact false. And so then the job in the second part of this problem is to figure out what was it about the Tn's, what was the important quality of the Tn's that made it possible for the product not to converge to 0 anymore, and then make a conjecture for how to fill in that blank and then to prove your claim. So this problem 3, we last saw problems of this type when we were talking about properties of sequences and how they relate to convergence. And it's set up in such a way so that the problem actually asks you to prove two things. Asks to prove that the sequence is monotonic and prove that the sequence is bounded. So really quickly, if we're going to prove that a sequence is monotonic, we have to make a choice, whether to prove that it's monotonically increasing or monotonically decreasing. So which one do you expect it to be for this sequence? Yeah, expect decreasing. And so then the statement that you would prove, I'm going to call this P of n, the nth proposition that you must prove for all natural numbers n, is that the n plus first term of this sequence is less than the nth term of this sequence. And so then in your induction, you'll prove the base case, P of 1, that S2 is less than S1. And then you'll also show that Pn implies Pn plus 1 in the induction. So the inductive proof is that Sn plus 2 is less than Sn plus 1, given that we assume Sn plus 1 is less than Sn. So that's the structure of the induction for the monotonic claim. Now for the bounded claim, similar to monotonic, we have to go one step further than the definition, and we have to propose or conjecture what might bound for this sequence be. So what's an example? If you handed in this problem a few minutes ago, what did you use for a bound in this proof? What's a safe upper bound for this sequence? 10? Sure. So you're making the claim there that every single term of this sequence is less than or equal to 10 in absolute value. And then, of course, that structure is your induction. So the nth proposition is that the absolute value of Sn is less than or equal to 10. The base case that you would have to establish directly is that the absolute value of the first term is less than or equal to 10. And the inductive case, we need to show that the nth term being bounded above by 10 implies that the n plus first term is bounded above by 10. And so there, the key, as with any induction proof, is to turn this claim that you're trying to prove about Sn plus 1 into a claim about Sn that you can then use the inductive hypothesis to justify. And the key tool in both of the inductive steps here is going to be the recursive definition of the terms of the sequence in terms of the previous term. So the last problem gives you a sequence that has some, what do you want to call it, two-faced behavior in a way. This sequence is interesting because of this minus 1 to the n term that appears here in the middle. Anytime a minus 1 to the n shows up in a formula for a sequence, that's an indicator that there might be different behavior for half of the sequence's terms compared to the other half. So how did you, when you did this problem, get a sense of what the terms of the sequence look like? Classic strategy for understanding a sequence is just to write down the first few of its terms and see if anything jumps out, see if a pattern jumps out that you can then maybe make a conjecture about. So if we look at terms 1 through 6, we'll notice what happens. That I'm going to not simplify the arithmetic really quick. I'm going to actually just write it all out in its glory. So the 1 over n's, the 1 over n's are just going to have the usual pattern that we're familiar with. 1, a half, a third, a fourth, a fifth, a sixth. Meanwhile, the minus 1 to the n's, what do those do as n starts from 1 and continues to 2 and so forth? Negative 1 to the first is going to give me negative 1. Negative 1 to the second is going to be positive 1. Negative 1 to the third is negative again. Positive, negative, positive. So I've got that minus 1 to the n term in the middle that's alternating around. And then I also, for all of my terms, I have this 1 at the beginning. 1, 1, 1, 1, 1, 1. Okay. So what pattern are we seeing emerge here in the first 6 terms? These orange terms are nice and predictable. What's happening with the reds and the blues? They're alternating between 0 and 2. Right. So another way to think about what this sequence is doing is that for all of the odd numbered indices, 1, 3, 5, 7, and so forth, 1 minus negative 1 to the n is giving me a 0. So if I just scrub that, just think of it as a 0 right there. Same thing with this one, same thing with that one. Meanwhile, the even index terms are all giving me a 1 plus 1, which in most math classes is equal to 2. Yeah, I think something's amiss here. Yeah, you're right, because it was minus there instead of a plus. Sorry. Okay, let's get that all fixed. So that's 1 minus negative 1 to the n. So that becomes a minus there, and a plus, a minus there, a plus here, a minus there, a plus here, and a minus there. Right. So I get a 2 in my a 2 in my odds, and a 0 in my evens. 0 there, and a 0 in the fourth and the sixth, and a 2 in the third and the fifth. So one way of understanding the sequence is that we have this nice predictable behavior for all of the odd index terms. Let's call those, so let's talk about subsequences here for a minute. If I create a new index, I call it k, then I can index my odd terms by n sub k is equal to, what would it be, 2k minus 1. I think is going to give me this association. So the k is 1 means n is 1, k is 2, n is 3, k is 3, n is 5, and so forth. And in that case, what I would do then is I would plug that index into the formula for my sequence, get 1 minus negative 1 to the 2k minus 1, minus, and there's, wait, no, it's a plus, sorry, plus 1 over 2k minus 1. And then I would just simplify this out by observing that negative 1 to an odd power is always equal to 2. And so therefore, 1 minus negative 1 to that odd power is equal to 2. And that's just going to let me rewrite the formula for that sequence as 2 plus 1 over 2k minus 1. I would call that the sequence S sub 2k minus 1. And you can imagine how a similar process would quantify my subsequence consisting of the even index terms, so that the first term of the subsequence is the second term of the original, the second term of the subsequence is the fourth term of the original, the third term is the sixth, and so on. And so for that subsequence, we can write that as S2k. There you would convince yourself that a formula for S2k is 0 plus 1 over 2k. And since these two subsequences partition the entire sequence Sn, right? If I take the odds and evens together, I get the whole parent sequence back. The notion is that those two subsequences can tell me everything that I want to know about the limiting behavior that lives within this parent sequence. So the question I want to ask, just to wrap this up, is based on this information, what do we think is the limit set for this sequence? What are all of the limits of convergent subsequences of this Sn going to look like? Zero and 2. So I have my even index subsequence that as k tends to infinity, 1 over 2k is going to vanish, and the limit of that subsequence is going to be 0. I also have my odd index subsequence, where as k tends to infinity there, 1 over 2k minus 1 is going to tend to 0 also, and that limit is going to be 2. And because those two subsequences partition my entire sequence, those are going to be the only two limits of convergent subsequences that live within this parent sequence. And because of the way that we've defined limit supremum, limit infimum, those limiting concepts in 2x, because of the way that we've defined those, once we know the limit set, we kind of know everything that we need to know about lim sup and limit. And so then what I'm asking you to do on this problem is to think back to the conversation that we had last Wednesday about the difference between the lim sup of a sequence, the limit supremum, and the sup of the sequence. So the lim sup being a statement about the asymptotic behavior, the behavior as we tend out towards infinity, and the supremum being a claim that we make about all terms in the sequence, and trying to differentiate between what those two things are saying.